Hi everyone, welcome back to the CogArch 2022. Um, our next talk is by Professor Tahana Roseng. She's a professor, a holder of the Fratamico Endowed Chair, ACM and IEEE Fellow, and a director of the System Energy Efficiency Lab at UCSD. Her research interests are in energy efficient computing, computer architecture, distributed systems. Prior to coming to UCSD, she was a research scientist at HP Labs, while also leading research efforts at Stanford University. She finished her PhD in EE in 2001 at Stanford, concurrently with finishing her master's in engineering management. Prior to pursuing her PhD, she works as a senior design engineer at Altera Corporation. And with that, I welcome Professor Tahana Roseng.
Wonderful, thank you so much. And I should let you all know that most of what I'm presenting today is Saransh's work. So maybe we should really switch seats, Saransh. Thank you for the introduction. So today I'll be talking about end-to-end computing with fully homomorphic encryption in memory. As I said, this work was done primarily by Saransh while he was still at UCSD. He's now at IBM Research, and we continue to collaborate. It is also done jointly with Rok Hamarota from Intel Labs, and it was sponsored by SRC. So why are we concerned about data privacy? Well, one of the reasons why we should be concerned is that there have been a lot of data breaches. In fact, in 2017, there were about 800 breaches, which actually cost people almost $13 million. And more recently, in 2019, about 4 billion records were breached. And the price tag with these breaches is ever growing. So we really need to rethink data privacy. Instead of just relying on the classical schemes where we're relying on data to be encrypted when it's being sent to the cloud, and then cloud has to decrypt it and operate on it, what we really should be thinking about is computing that is ultimately based on full privacy, where the cloud and nobody other than us ever sees the data in the raw form. So I already alluded to where we are today in terms of traditional secure computing. What happens today is that the cloud has secret keys for the clients, and the clients will encrypt the data using the key, send it to the cloud will decrypt it, and then operate on it. So both the secret keys themselves are prone to attack, and also data can leak at the cloud itself because it is in the raw form when it's being operated on. What we would like to do instead is we would like to run homomorphic encryption. In this case, cloud would not have the secret keys, and full processing would happen on fully encrypted data. So data never gets decrypted in the cloud. This means that you can run as sensitive data as you want without having to be afraid of the data being breached. And this is frankly a huge deal in areas such as medicine or finance, where we want to really be very protective of our information. So if you look at historically what has been there in terms of homomorphic encryption, there's been partial homomorphic encryption, where you would have some small subset of operations that you can run on data text, usually either only addition or multiplication. Then there is something that's kind of in between, where you can do both addition and multiplication operations, but you can do it for only few computations. And then finally, there is fully homomorphic encryption, where you can do both addition and multiplication, and there is no limitation on the number of computations. So really what we would like to focus on now is on fully homomorphic encryption, because that gives us the best protection. In the first generation homomorphic schemes, bootstrapping, which is a procedure that you need to actually recover some of the errors that come in during the computation, is very, very slow. So it's completely unrealistic to use. In the second generation, what happens is people are using leveled homomorphic encryption. So they actually use fairly large parameters that allows them to avoid bootstrapping, but that means also that you're a little bit limited in how many and what type of operations you can do before you start getting large errors. And we try to amortize latency. So one of the nice things about second generation is that it does allow packing. PVW method of packing provides ability to put many plain text elements in a single larger type ciphertext, and that can be used to perform SIMD homomorphic operations on the packed ciphertext. This is an alternative to smart Verkuten cipher packing technique, which relies on polynomial CRT. Third generation and beyond is really what we're most interested in. It leverages ring GSW-based fast bootstrapping. It does encrypt at the bit level. You can do arbitrary function, but the cost of it is that you end up with pretty high total latency. So if we look at a simple operation, and in this example, if I just have a single integer a, and I now encrypt it, I end up with ciphertext that has a polynomial and an integer. So I end up with polynomial that is of the degree that may be greater than 512, and coefficients are bigger than 8 per each, which means that I go from data size that's relatively small to something that's easily bigger than 20 kilobytes. So the data size is really exploding. For multiplication, it's even worse. We now have to multiply polynomials instead of just normal integers. So we end up with a whole pipeline of operations that has to be actually done before we can get the result. So instead of a single multiply operation, we now have more than 10 million operations. So it's pretty clear that you would expect computing in third generation fully homomorphic encrypted domain to be much slower and to require much larger memory size. And then it shouldn't be a surprise when we look at state-of-the-art implementation, such as Microsoft CL Library, and you apply fully homomorphic encryption on it to do MNIST-based training, where you have tens to hundreds of megabytes of data for about 60,000 images, you find that encryption and decryption takes so long that it's completely unrealistic. Here we're talking about on a small device, as long as 14 days, on a server, almost a day to just do the encryption. So really, we need to solve this problem. And most of this problem really is due to the fact that the data has exploded, while we need to do lots of relatively simple add and multiply operations on those data. So the problem with today's systems is that there is this huge gap between the CPU speed and the memory performance. And this gap has been growing wider with each decade. So if we look in today's systems, the capacity has actually grown quite dramatically by 128x over the last few decades. However, the bandwidth has grown only 20 times over the same time, and unfortunately, latency improved barely by 30%. And we do not really expect latency to improve a whole lot faster. So you can see that it's pretty clear that we're going to need new hardware architectures to deal with the big data that fully homomorphic encryption brings. So traditionally, when people think about processing in memory, the idea is to, instead of taking lots of data out of the memory and moving it to the processor, to instead enable memory to have some computing capabilities. And this has historically been done in a couple of different ways. One way is to do what we call near data computing, where you have lots of memory. So in this example is DRAM dies. And at the bottom of it, in three-dimensional stack, you may have some simple logic computing, which then interacts with the host CPU. So all of the simple operations that can be done on the logic die are done prior to moving any of the results to the CPU. The nice thing here is locally you get very high bandwidth through the TSVs, but the interval operations are fairly expensive and they're relatively limited in what you can do. Another way that people have done this is by using analog processing in memory, which basically means that you have to have analog to digital conversion and digital to analog conversion. And what I'm showing here is an example design that uses MEM-resistive devices. So the problem with analog PIM is that you end up with having up to 90% of the area that is dedicated just to digital to analog and analog to digital conversion. You can get fairly fast vector matrix multiply, but it comes at pretty high cost, and the operations you get are fairly limited. So what we like a little more is what we call digital PIM, where the level of voltage actually determines the type of function that you're going to get. What's nice about this is it has minimal area overhead. There is no analog to digital conversion, and you can implement lots of different operations using it. So if we do digital processing in memory, what we're looking at is resistive RAM organized in multiple blocks where different blocks may perform different types of functionality. Functionality that you can implement includes bitwise operations such as NOR and XOR and so on, arithmetic operations such as addition and multiplication. And this then gives us ability to actually perform most of the operations that we would need for our fully homomorphic encryption. The advantage is that here the data stays where it is, so you don't have to pay the high cost of moving the data. Because we have a lot of parallel blocks, we can actually get very high throughput by leveraging this high parallelism. And it's pretty easy to scale. You just need to add more memory chips, and that gives you actually then scalability in the sizes of data. So some examples of operations that we do using this kind of implementation. As a baseline, we have a typical NOR operation. Using baseline bitwise operations, we can implement row parallel addition and row parallel multiplication. And obviously, you can always do row parallel binary operations as well. So this effectively provides us with the ability to do very fast entity transforms as compared to what is done on the typical server. And you can see on the left for polynomial of degree n on the server, as the degree grows, you end up with very, very low throughput. Versus in processing in memory, you can actually push this degree pretty high before you see a hit. And the hit you see primarily because we now need more memory and more chips to actually make it work. So this is an excellent example of why you would want to implement very high throughput, highly parallel polynomial multiplication using processing in memory design. So what we did and what Saransh designed is an implementation of a third generation fully homomorphic encryption that is based on FHEW work done by Daniela at UCSD. In our design, which we called MEMFHE, we provided end-to-end privacy-preserving computing system that has both client and server implementations. Our architecture, as I said, is based on the work done by Daniela, which provides the slowest noise growth. And that is why it is best for all of the, given all of the different types of fully homomorphic encryption. It is implemented completely in memory using crossbar arrays and exploits digital PIM design to implement all of the operations. All computation in MEMFHE server happen in the encrypted domain. The server utilizes bootstrapping to reduce the noise, which bootstrapping happens to be the most important, but also the slowest process in our pipeline because it is fairly iterative in nature. So what we did to optimize it, we tried to pipeline it as much as we could. So that way bootstrapping is split over multiple pipeline stages. We also introduced novel architectures for various subcomponents of bootstrapping and perform operation level optimizations in the bootstrapping core. And the result is that our MEMFHE server can achieve a throughput of about 170 inputs per millisecond, even for high security parameters, which is about 20,000 times higher than what is possible on CPU for exactly the same algorithm. We also designed the MEMFHE client, which provides input ciphertext and receives the output of the server. It is done, as you can see, by pipeline resistive RAM operations in memory. The client is responsible for converting raw data into FHE domain using client-specific secret key. The client in FHE crypto system will encrypt a bit of data into an LWE ciphertext. MEMFHE client accelerates AWE utilizing efficient in-memory multiply accumulation and shift operations. The encrypted ciphertext is sent to the server along with an encrypted version of the client's secret key. Client will also decrypt the output of FHE computation from the server into plain text form. So what I would like to do next is kind of step through these different operations one by one. So our system takes input bits and represents them using ciphertext for each function. That should be applied on the input ciphertext. FHEW stores a corresponding FHE function in the lookup tables. So for example, an AND operation between two bits in plain text translates to a simple addition of their corresponding ciphertext followed by AND specific coefficient mapping. This then will be followed by bootstrapping, which reduces the noise accumulated in the output ciphertext due to a function implementation. If we did not bootstrap, the output ciphertext may become undecryptable. So without bootstrapping, you get in big trouble. The final output ciphertext with reduced noise is extracted out, and then it is treated with encrypted version of the secret key to convert it back to the original learning with error encrypted domain. This process is called key switching. The key switch ciphertext is decrypted to get the final output. Bootstrapping itself consists of initialization, update, and extract steps. The length of the boxes pretty well represents the complexity and the latency of each of the operations. The two bootstrapping procedures that we deal with are AP and Jinx. The corresponding FHE schemes are FHEW and Jinx, and we support actually both of them. And as I said, bootstrapping will enable reliable FHE computation. And this then, unfortunately, because it's so high overhead, it is a performance bottleneck in the server. On top of that, applications will need potentially different bootstrapping procedures, so we have to support all of the different possible procedures. And in order to speed this up, we use the processing in memory implementation. So to look at a little bit more depth on what happens in the client, what we start out with on the client side is we encrypt the data and we send it to the server. The server then will use the universal function, or we call it here ufunc, memory block to execute polynomial additions and subtractions that are needed to implement the desired function. It then will input the result into a bootstrapping pipeline, which you can see here, which consists of multiple stages. And I'll talk about each of these stages in a minute. And then finally does the key switching and sends the result back to the client. So if we look at encryption and decryption in the client, the FHE client will apply learning with errors encryption on the message bit M. And here is what that procedure looks like. The encryption is performed for given application parameters Q and N, where N is the degree of the polynomial we use, and all operations and data then are taken modulus Q, which is the ciphertext modulus. When we decrypt basically going backwards from the encryption, as you can see here. So the dot product in the decryption is actually the slowest client operation. So if we look at how this is done in the client encryption converts a message bit M into a ciphertext of the type that has components A and B, where A is the integer polynomial of length N, so that's where that N parameter comes in, and B is the integer. This encryption utilizes learning with errors encryption technique. Generating integer B requires a dot product between vectors A and S, followed by adding E and M prime. To generate this dot product, we utilize secret key memory, skmem. It stores a vector corresponding to secret key in a row parallel way, such that all the elements of S occupy the same set of memory bit lines, and each element in S is stored in a different row. So the incoming vector A is written in such a way that the corresponding elements of A and S are present in the same row. So then we can implement row parallel integer multiplication between the elements of the two row vectors. And our row parallel execution will perform this row-wide multiplication with the same latency as the single multiplication. So once we have done that, we follow this by addition of all the products. To add, we perform column parallel in-memory addition operations on the output products using the in-memory switching instead of the sense amplifier-based operations. We accumulate each bit position independently so that n p-bit numbers are reduced to p log 2 n bit numbers after n minus 2 column parallel 1-bit additions for each of the p bit positions. To further reduce the output to a single number, we transpose the output of column parallel additions so that the outputs of all p columns are stored in the same row. It takes p data transfers, log to n bits per transfer to read the outputs column-wise and store them in a row. We then perform bit serial addition to obtain the final integer output, which takes p log to n 1-bit additions. This output represents the dot product a dot s, to which we add integers e and m prime. So this basically represents just one element of our process. We do this element multiple times in parallel across various memory blocks. So all of the further additions and subtractions are done for encryption and decryption as appropriate. So if you look at the server side, the main strength of FHEW lies in its ability to implement arbitrary functions. It achieves this by translating each Boolean function into one or more homomorphic computation steps, and then mapping the integer output to a bootstrapping compatible polynomial, which we call MB. Each element of MB is set to either Q divided by 8 or minus Q divided by 8, which are FHE equivalents of binary 1 and 0. So FHE allocates a memory block which stores these translations for all functions. And you can see some examples here for the functions and what their mapping looks like. Function implementation is the only process in MFHE server that follows the client's parameters. Remember, the client parameter n gave us the degree polynomial, and q basically was the modulus. FHEW uses polynomial addition, subtraction, and scaling by a constant as computing steps. So for example, an AND between 2 bits is implemented by first homomorphically adding the corresponding ciphertext, and you can see this in the first row of the table, followed by mapping the integer part of the output ciphertext to n-degree polynomial MB. Then each coefficient of MB in the final result, which you can see here in the table, is set to either Q divided by 8, and the others are set to minus Q divided by 8. To implement this mapping operation in parallel for all coefficients, we utilize search-based PIM operation. Using exact bitwise search operations, MemFHE implements in-memory compare operation, which can search a set of memory columns for all the numbers greater, equal, or less than the query. First, we input lower bound as a query and search for all the numbers greater than the lower bound. Then MemFHE performs searches for the numbers less than the upper bound. The final filtered out rows are initialized to Q divided by 8, while the remaining rows are initialized to minus Q divided by 8. The resultant noisy C output, which you can see up coming out of the function, is the initial bootstrapping accumulator value, which goes into the bootstrapping. So if we look at the bootstrapping, it is used to reduce the noise in the encrypted data, which enables FHE computation. It is also the main bottleneck. And as I said before, applications will likely need different bootstrapping procedures. So MemFHE supports 2 types of accumulation schemes, AP and Jinx. And you can see that they have different trade-offs in terms of runtime and the key size. While Jinx is more efficient for binary and ternary distributed secret keys, AP is more efficient in all other cases. So that is why we support both. So if you look inside of the bootstrapping, bootstrapping is iterative, and it inputs the encrypted ciphertext and performs the desired operations on the ciphertext in its basic function unit, which we call ufunc, without decrypting them. So computing in FHE domain leads to the accumulation of noise in the resultant ciphertext. So if we go into the bootstrapping process, we start first with key generation, and then we move to initialization, update, and extract steps. A typical accumulation, which is done iteratively in bootstrapping, needs more than 1,000 sequential iterations. Each iteration is a set of polynomial multiplications. So as a result, we use a pipeline for different accumulation and multiplication stages in order to speed up this process. The initialization phase of bootstrapping converts the output of universal function unit into a server-compatible encryption and initializes a cryptographic accumulator, ACC, in this figure. Then bootstrapping will use a series of accumulation units, which are in green boxes labeled UACC, to modify the contents of accumulation. The accumulation uses EKB to decrypt away the accumulated noise from the output of the universal function unit. The inputs to the accumulation function include the decomposed representation of A and RGSW encrypted refreshing key EKB, and the outputs of initialization step, which are pair of polynomials of degree n. Accumulation performs iterative multiplication of this key with ACC and then additions back to the ACC. And this turns out is the slowest part of the bootstrapping due to the high data dependency between the iterations. That's the result of the multiplication in each iteration to the accumulator. The dependency of the input of one ciphertext element to the output of the previous one further prohibits the functions from being parallelized across the ciphertext elements. But each ciphertext element is a high degree polynomial, which allows us to parallelize over the polynomial length. So here we designed bootstrapping pipelines so that the accumulation logic consists of n times dr accumulation units, which are labeled in green boxes. And inside of each unit, we then further perform highly pipeline parallel iterations of polynomial multiply accumulates. So this allows us to actually get a much more efficient implementation than otherwise would have been possible. And to make the multiplication efficient, all of the polynomials are converted in entity domain before multiplying and then converting them back. So as I said, we use entity, which is number theoretic transform, to convert the data and to do the polynomial multiplication, which then becomes element-wise multiplication. So this is what happens effectively in entity domain. Entity is a generalization of fast Fourier transform that performs transformation over a ring instead of complex numbers. So the process of converting to and from an entity domain is quite complex. The state-of-the-art implementations use algorithms where the coefficient access pattern for an n-degree polynomial changes for each of the log to n stages of the entity pipeline. So this results in irregular interstage mapping. Instead, we use Singleton's FFT algorithm, since the coefficient access pattern for this Singleton's algorithm remains the same for every stage. So then MEMFHE will use this to avoid having to have super specialized interconnects. The problem with this is that we have to store more entity parameters. So if we look at the figure, we start from the Singleton's FFT algorithm to implement. The figure shows the data layout of one entity stage in MEMFHE. We write an n-degree input polynomial, A, in n divided by 2 rows, so that the pair of coefficients with indexes 2i and 2i plus 1, so odd and even, share the ith row of the memory block. All such pairs are written in separate rows utilizing the same columns. We use a twiddle factor with each pair, which is pre-computed and stored in the corresponding row. Each pair generates the ith and I plus n divided by 2 coefficients of the output polynomial in the ith row of the block. And then each entity stage of MEMFHE performs 3 compute operations. First, we have a row parallel multiplication between the 2 coefficients with odd indexes and the corresponding twiddle factor. Then we add the generated products to the coefficients with even indices in row parallel way to generate the first n over 2 coefficients of the output polynomial. Lastly, we subtract the products from the even index coefficients in row parallel way to obtain the remaining output coefficients. The bottom figure shows the data transferred in each transfer phase. We perform column-wise data transfer where each column consists of 1 bit from all rows of the memory block. The output polynomial is present in n over 2 rows so that indexes are stored in one set of columns and the remaining indexes in the other set of columns. So we need about 4 data transfer phases to do this. These data transfers read selected rows from one memory block, send it over a conventional local interconnect, and write them at contiguous location of destination in memory. Entity and the inverse entity use the same hardware and have identical data mapping, computation, transfer, and pipelining schemes. They differ only in the twiddle factors, W's, that they use. So during the pre-compute step, the inverse entity pipeline generates the twiddle factors, which are inverse of those used in entity. The rest of it is completely the same. So in order to implement our design, the butterfly-based FFT computations would involve up or down shifting inputs by a constant factor S. So MEMFHE uses specialized switches for shifts. So instead of doing it in this way, what we do is we implement our switches using simple transistors to do the downshift and to do the upshift, as you can see on this figure. So putting it all together, which was not, and this work was actually nominated as the best paper at BAC. We distribute each entity stage over multiple pin blocks with separate multiplication and following modulo operations. And you can see how these blocks connect. And what we found is that our entity PIM implementation has about 40% faster throughput than a naive implementation would for the polynomial degree of 1024. So going back to our server computations, after accumulation, we perform extraction, which is a simple mapping process that converts these polynomials to ciphertext. The first polynomial of ACC represents the polynomial part of the bootstrapped output ciphertext. The constant term of the second polynomial represents the integer part. So to reverse the mapping, we effectively need to do the q divided by 8 will be added to modulo q to the integer part. After bootstrapping is completed, key switching is performed to obtain output encrypted with S so that it can be decrypted by the client. And this utilizes switching key EKS, which is sent by the client to the server, along with refreshing key EKB. So the latency here of polynomial add is fairly small as compared to the polynomial multiply. So this is why we did pipelining of multiplication using the entity transform. So now that we've put it all together, we can start evaluating different components. To evaluate, we implemented the C++ cycle accurate simulator. We also simulated circle level design in 28 nanometer CMOS, and we used BTM memory store model for the resistive RAM component. We compared to FHE-enabled neural network that runs on CPU, and we compare it in a couple of different modes. We show our CPU implementation, which we refer to as TFHE based on DNN. TDNN converts DNN operations into TFHE compatible functions. We use the same functions to evaluate MEMFHE as it supports TFHE. TDNN works in both fully homomorphic, which is labeled as TDNN-FHE mode, as well as a leveled mode, which is labeled as TDNN-LVL. While TDNN-FHE bootstraps each gate operation, the leveled bootstraps only higher level operations like polynomial multiplication and addition. MEMFHE provides a range of classical and quantum safe security guarantees, but TDNN only provides 163-bit or 125-bit security guarantee in FHE mode. So 163-bit is in FHE, 152-bit is in leveled mode. First, to compare the entity implementation, you can see that our entity implemented in PIM has 55 times higher throughput than if we were implementing it on FPGA, and it's way faster, like 225 times faster than doing it in software. It's 225 times more energy efficient and almost 200 times better throughput than software. So we also compared the server. And to get a better comparison, we implemented two different types of MEMFHE. One was throughput optimized, the other one was area optimized. We found that area optimized MEMFHE pipeline consumes 2.5 times less memory resources on average as compared to the throughput optimized design, but it reduces the throughput approximately 2.5 times. Latency increases by 75%, of which 98% is due to accumulation. This occurs because we reduce the number of pipeline stages by 3 times in area optimized design, but at the same time increase the latency of each pipeline stage by 2.2 times. Total energy consumption is similar between the two designs because they have the same number of operation. In contrast, throughput optimized design provides a throughput of 174 inputs per millisecond for 128-bit classical security and 51 inputs per millisecond for quantum safe security. Throughput varies with log2 of q squared, which is same as multiplication latency that happens to be the slowest operation in the pipeline. MEMFHE server takes 29 milliseconds to process an input and generates the output ciphertext for a client in 128-bit classical regime, but it takes 55 milliseconds to process in quantum safe FHE setting. Obviously, quantum safe design will have higher energy consumption. So if we look at latency and energy consumption of MEMFHE client, we can see that encrypting a bit to 128-bit quantum safe ciphertext takes 3 microseconds and consumes 4 nanojoules of energy. And you can see that clearly the results will depend strongly on ciphertext modules and polynomial degree of n. The MEMFHE client throughput is very scalable depending on the memory size. You can see that it increases mostly linearly with the increase in memory size. And the exciting part is that the throughput will actually go up to as high as well over 100 inputs per microsecond. If we look at arithmetic operations, the end-to-end latency of implementing additions and multiplications in MEMFHE is relatively high, but it's still much lower than what would happen on the CPU. We can run easily 1,000 independent operations in parallel to utilize best MEMFHE pipeline efficiently. So if we run around 1,000 of them, we are 20,000 times faster than CPU. If we run only one, we're 165 times faster than CPU. So this basically shows us that we can pretty easily get very high throughput, which is something that is really important when we're trying to accelerate learning in using fully homomorphic encryption. So to show you results on learning, I wanted to remind you that MEMFHE will accelerate the encryption, but does not address the question of how to make this efficient on low power devices. DNNs have made very impressive results in many fields, but the problem is that with DNNs, the performance is very reliant on hyperparameter tuning, and training really consumes a lot of resources. So it is very difficult to do full training in encrypted domain on a client device because of the humongous overhead that DNNs have during the training. So if we look at just learning using MEMFHE, you can see a comparison here with the published DNN work that uses both fully homomorphic encryption, but only 163-bit, or that uses only leveled encryption, and in this case, 152-bit version. And you can see that our design, if we utilize 1 terabyte implementation, we're about 18 times higher throughput than the 64 gigabyte version of our design. But if we compare the 64 gigabyte version to the fully homomorphic version of TDNN, we find that we have a 2,000 times higher throughput than the state of the art. A better way to implement fully homomorphic learning would be to go with very low complexity and still fairly accurate alternative to neural networks, which is hyperdimensional computing. So hyperdimensional computing leverages the fact that dense sensory input is often mapped into a high dimensional sparse representation in brain. We use this from the observations in biology to create a system that encodes all of the raw data into hypervectors, which are often vectors that have as many as 10,000 or more bits. So in this picture, you can see an example of encoding a black color in one large hypervector and white color in another large hypervector. To process these hypervectors, we need a relatively simple set of operations. We use addition, multiplication, and permutation to basically perform all of the learning operations, including we also use search when we do the inference. So this type of learning can be done very quickly because it involves very fast single pass training. In fact, for training, all you have to do is a simple addition. So this means that we can very easily do real-time learning, and it is actually relatively simple to get very high performance and good accuracy in fully homomorphic domain when using hyperdimensional computing. An additional advantage of hyperdimensional computing is that we get very high energy efficiency and very large robustness, which is a nice match for the issues that we get with needing bootstrapping for most of the other techniques. We have implemented a lot of different types of applications using hyperdimensional computing, including classification, clustering, regression, recommendation systems, reinforcement learning, federated learning, and many others. So in HD computing, we encode data into hypervectors to create a class hypervector. We just have to add all of the data together. So in this example, we would have individual hypervectors for each of the cat images, and we would add them together and then use thresholding to get a cat class hypervector. We do the same thing for the dog class. And then for inference, we encode the data, create a query hypervector, and do a simple similarity check. So if we use just binary data, then this is Hamming distance. We found that our accuracy is actually very good and very comparable to DNN, but we're much smaller than a DNN when implemented on the FPGA. And furthermore, we're much more robust. You can see here that with low SNR, HD computing in both binary and integer doesn't actually even notice errors, whereas deep neural network essentially crashes very quickly. And you can see that we can easily trade off accuracy with dimensionality, even in very high bit error rates for both classification and clustering, by simply changing how many bits we use when we encode. We can also get pretty impressive efficiency improvements when we implement HD computing using processing in memory. So in these results, we compared everything to CPU implementation, and you can see that both implementation in memory for classification and for clustering is much faster than running on CPU. And I should also note that implementation on GPU and FPGA were actual measurements on GPU and FPGA. So putting it all together, we can combine both deep neural networks and hyperdimensional computing. And when we put it all together, just to remind you, we had with deep neural network about 36,000 times higher throughput than the fully homomorphic encryption version of deep neural network. And in quantum safe mode, we're 15,000 times higher throughput. If we add to this and use the hyperdimensional computing instead, we now add another 30x improvement over the 30,000 times. So we're talking million times faster. So putting it all together, you have seen that we can perform real-time secure learning with third generation fully homomorphic encryption. If we want super accurate image-based computation, which DNNs are really good at, you may want to do deep neural networks. For pretty much everything else, you really want to use hyperdimensional computing because it's much more efficient, much more robust to noise, and much faster. So really, this shows that we can compute at today's speeds, but with full privacy that the third generation fully homomorphic encryption provides us with. And just a few highlights. Our new PIM design is on average 2,000 times faster than CPU. For FHE-enabled DNNs, if we, as you saw, if we push actually into quantum mode, we get much higher throughputs. And if we add HD computing, we get another 30x improvement in throughput as compared to the DNN version. And all of this happens at comparable accuracy, but is much more robust to errors. So I want to thank you all for your attention. And I think we might have a half a minute for a question.
Thank you, Professor Rosing, for the amazing talk. Any quick questions? I can probably pose a short question. So in your talk, you talked about an FHE algorithm, which is somewhat different from what the previous talks talked about, that it focuses on bit operations instead of arithmetic operation. Are there any obvious benefits in doing that? Or are there any particular applications that you feel would be more suited to these kinds of schemes?
Yeah, that's a good question. So this particular scheme is a little bit more complex in the sense that it has relatively lower throughput if you implement it on the CPU, because everything has to be implemented at the bitwise level. But the huge benefit is that you can implement any function and you can get very high accuracy. And as you saw in my talk, if we speed it up using in-memory compute, we end up with very high throughput. So really you get the best security, which actually has been published in, I want to say, last year's crypto. It has shown that, in fact, this third generation FHE schemes provide full security, whereas schemes such as CKKS actually do have some liabilities. And it provides us with the ability to get reliable and safe computing that does not have high errors, that actually provides pretty high accuracy as well. And if we combine it with techniques such as hyperdimensional computing, we can also implement systems that learn even in very lightweight clients very accurately and faster, and are more energy efficient than state-of-the-art DNNs can do. So I think it provides really the best of all worlds.
Thank you so much, Professor. Let's applaud the speaker, and we can move on to the next talk. Thank you so much.
Thanks. Bye.